Today we're going to be talking about precipitation reactions, and precipitation reactions are a type of double replacement reaction where one product is insoluble. So remember double replacement reactions, that's where we referred to them affectionately as either permanent swingers or wife swap. And so we can see it here. This is a double replacement reaction. We have A and B. They were dating until they met with C and D. And then A thought that D was hotter than B, so they got together. And C thought that B was hotter than D, so they got together. So since they switched partners, and one of those products is solid, that is a precipitation reaction. Now those little cue cards, they're called state signifiers, and AQ means aqueous. It means that the compound that we are referring to is soluble and is dissolved in a solvent. Okay, so for precipitation reactions, the reactants have to be aqueous. If they are not aqueous, you cannot form a precipitation reaction. The little s means that it is solid and it is therefore insoluble inside of that reaction. So what we're going to do now is we are going to go ahead and utilize this format to help us predict products from a precipitation reaction and actually see if something is going to be soluble or not. So we're going to first need to be able to recall the law of conservation of mass. And remember that that tells us that everything on one side of the reaction is going to have to be on the other side of the reaction. Okay, so if I have this example reaction, I have barium carbonate, which is aqueous, and it is reacting with sodium sulfate, which is also aqueous. Remember that the reactants both have to be aqueous in order for it to be a valid precipitation reaction. So I am asking, how in the world do I know what the products are? We know that it's going to be a precipitation reaction, and we know it's going to be a double replacement reaction because double replacement reaction is an overarching name for a precipitation reaction. So the first thing that we're going to do is we are going to identify our anions. Those are the ones who are going to switch places. You should be very good at identifying anions now, as you've had to identify the anion for every single one of your solubility problems. So it should be very comfortable for you. Remember that the anion will come second. The bad guy is going to creep behind the good guy, the positive one. And so I went ahead and I identified that carbonate was going to be my anion for barium carbonate, and sodium was going to be my anion for sodium sulfate. Now that I have my anions identified, I can go ahead and check my charges and switch my partners. What I mean by check my charges is because these are ionic compounds, they have to be neutral whenever they are actually inside of a compound. So we need for the amount of positive to counteract the amount of negative. So whenever I see barium, I see that it is +2. I know that it is +2 because on the periodic table, when I find barium, it is in column 2, and therefore it has 2 valence electrons. It's going to give away those 2 valence electrons, and giving a gift is a nice thing to do, so its charge will be +2. As for sulfate, I know that sulfate is going to have a charge of -2 because on my list of polyatomic ions, or in the list for the solubility rules, I see that sulfate has a charge of -2. Now, why did I pair barium and sulfate together? That's because I know that barium is going to leave carbonate and get with sulfate. So I'm going to go ahead and compare those. I see that +2 and -2 cancel. That leaves me with a neutral charge. So I can go ahead and just say that those are going to be partners together, just straight up. I don't have to have any extra bariums to cancel out the sulfate charge. I don't have to have any extra sulfates to cancel out the barium charge. So we're good with just BaSO4 for barium sulfate. Next, I know that sodium is going to be getting with carbonate, and so I'm going to go ahead and write down their ion form. I have sodium. I have identified it as having a charge of +1. That is because sodium is in column 1. It has 1 valence electron, therefore it will give away 1 valence electron. Giving a gift is a nice thing to do, so it's a positive 1 charge. Whereas carbonate is a polyatomic ion, so we have 2 places that we could find out about carbonate. We could find it in the polyatomic ion list, or we could look for CO3. Carbonate is here. It has a charge of -2, so I've identified that it has a charge of -2 here. Now this one is not immediately canceled out like barium sulfate was. For sodium carbonate, I need to cancel out this charge. I need to have as much positive as I do negative. The least common multiple between sodium and carbonate is 2. So that means I need 2 sodium atoms to counteract the carbonate's negative charge. So I end up with a formula of Na2CO3. Another way that you could have done this is you could have exchanged charges for subscripts. Carbonate's charge 2 became sodium's subscript. Sodium's charge 1 became carbonate subscript, but we don't write ones, so it was just left alone. Now if I had had multiple carbonates, then I would have had to have parentheses around those, but I don't, so we're all good there. Now we're just gonna go ahead and take these new products that we've just created and write them into our equation. And finally, we need to go ahead and check solubility and assign state signifiers. So I need to see if barium sulfate is soluble. So I'm gonna go ahead and I'm gonna look it up by sulfate. Sulfate is in the generally soluble category unless it's bonded with barium. So that is going to be my insoluble compound. So I will attach the state signifier S for it being solid. And my other compound is sodium carbonate. I will check to see if sodium carbonate is soluble. I see carbonate is in the generally insoluble category unless it's bonded with ammonia or an alkali metal. I need to make sure if sodium is an alkali metal. Whenever I look at the periodic table, I see that sodium is in the first column. That's where the alkali metals live, which would make carbonate break the rule. So this carbonate will be soluble. So I went ahead and I added it there. It does look like I forgot to add the state signifier for sodium carbonate, so I will do so now. And I am done.